Welcome back. So, if you recall, in the last lecture we had introduced the different types of applications in which transistors are used, and we started with power switch, a transistor used as a power switch in the area of power electronics. It's a very expanding a application and a market. Most of the things that we see around where power conversion is needed actually use a transistors as switch to make the circuits. Okay, and we discussed about some of the parameters that are important. What are the considerations we should keep in mind in terms of discussing power transistors? Like the most important are breakdown voltage and on resistance. Things like gain or saturation of current are not important for power switch. What is important is the on resistance and the breakdown voltage, right? A transistor has to act as a switch, right? So, I told you that dominant technology is silicon, but there are upcoming technologies like silicon carbide, gallium nitride, which are also offering much better solutions. And you might wonder, where are these applications that are actually using these technologies? You might think of a laptop which you plug into the wall plug socket that has 220 volt voltage, but the laptop is charged at 20 volts. So, you have to convert that 220 volt to 20 volt from AC to DC, because the laptop charges in DC. Same with mobile phones, which use a 5 volt line, DC line. So, you have to convert the 220 volt AC on your wall plug socket to a 5 volt DC. So, you have to step down the voltage. So, all these conversions from AC to DC, DC to DC and so on, stepping down, are done using power electronic switches and circuits, and these are made of transistors and diodes. Okay, so that's why the on resistance and breakdown voltage of transistor switches are very important. We'll continue from there. We'll come to the whiteboard, and as we recap the last lecture, if you recall, a transistor as a switch, right? So, a transistor as a switch has to essentially allow, when it is on, I am putting the output current, and here I am plotting the output voltage. When it is on, it has to conduct very high current at very low voltage, okay, like that. And when it is off, it should block very large voltages at very low current. Okay, so breakdown voltage is here, and the slope here is basically 1 by the resistance. Okay, you want the on resistance to be very slow, which means at very small voltage like 0.1 volt drop, you are able to carry very high current. It's almost like metal. Okay, and at very large voltage also, you are basically blocking it in the off state. So, that will behave like an insulator. In a way, a transistor switch should go ideally from like a metal to an insulator. It should be able to carry very high current in the on state and very low current in the off state. Okay, so it's like a switch, right? So, you have a switch here. The switch will on and off. When it is off, it should block a large amount of current. When it is on, it should conduct a large amount of current. When it is off, it should block a large amount of voltage. When it is on, it should be able to carry large amount of current without much voltage drop here. Okay, when it is on, when the switch is closed. Okay, so that's why the breakdown voltage should be high and the on resistance should be low in order for a transistor to behave like a good switch. Okay, and it should be able to move that fast. Okay, so when, for example, the current when the current is for example, if you have a voltage and a current, if I plot the voltage and the current waveforms. Okay, if you want to plot the current and the voltage waveforms, so here I am plotting, for example, the current waveform across a switch, and here, for example, I am plotting a voltage waveform across a switch, and this is with respect to time, by the way. Okay, time, you have to switch it very fast either. So, when the voltage is in the off state, I'll use another color. When the voltage, you are going to use you're going to have very high current. You're going to have very high current. In that window, the voltage drop should be very low, very low. And when the ideally, the voltage drop should be 0 across the switch when the current is very high, and when the current comes down to 0, matlab it's completely open circuit, the voltage blocking should come up high. This is the reverse bias voltage, whatever breakdown voltage you give, it should be like that, right? And again, when the current rises up, the voltage should come down, and so on and so forth, right? That is an ideal switch. But in reality, an ideal switch doesn't exist ideally, and so the transistors have their own finite behavior. That's what we were talking about in the last class. So, in what happens in reality is that this is your time, this is your current, this is your time, and this is your voltage across the switch, this is your time. In reality, what happens is that when your current is high and you are carrying, say, maybe 5 amperes or 10 amperes of current, ideally your voltage should be 0 across the switch. It should not drop any voltage, but there is a small finite voltage drop, that is a V forward drop, that will happen. Okay, and then the current will fall not instantaneously. The moment you switch, you change the voltage, you change the voltage will take some time to rise. in that time the current will take some time to fall, and the current will not come to 0 exactly. There will be a small leakage in the background. The voltage has come up here. Again, when you switch off the voltage, it will take some time to come, and the current will take some time to turn on, right. So you see this current is there which is very high, maybe forward current IF, maybe 10 amps, 5 amps, 1 amps, whatever. Ideally this voltage drop here should be 0, but in reality there is a small finite voltage drop. So the product of this forward voltage drop with the forward current that you are carrying, this is supposed to be, this is very high, say 5 amp or 10 amp or whatever. This is supposed to be 0, but it actually not 0. It's probably like 0.1 volt or whatever, small voltage will drop. The product of this will actually give you the power loss during the on state. This is the on state power loss, because you are losing some power because of the product there, right. Similarly, in this state the current should be ideally 0 when it switches off. The voltage should be high as the breakdown voltage here, but actually the current is not 0. There is a small amount of leakage current that goes. I can call it IL, leakage current. So IL times this VR, whatever reverse voltage you are blocking, the product gives you the offset current loss, offset voltage loss, sorry. So there is a, this also offset power loss, sorry. There is a power loss in the offset, there is a power loss in the on state. These actually are finite losses that you want to minimize. And if you see the transient, there is always this transient where the current is decreasing gradually, the voltage is increasing gradually. So the product of this and this, the product of this and this also is not 0. It also has a peak small there, and that is called switching loss, or the transient loss, the switching transient loss. Similarly here, the product of this and product of this, because they are in the same time zone, one function is going like this, one function is coming like this, the product of that will also be very important, and that's called switching loss. And the switching loss depends on frequency. If you are switching it very fast, then the switching loss also will increase, okay. So these are the 3 types of losses, nevertheless we should be generally aware of. And I told you that one of the important things is that there is called Baliga figure of merit, okay, Baliga figure of merit, which essentially relates the on resistance and the breakdown voltage. So it says that the breakdown voltage divided by the on resistance is actually constant, which depends on the dielectric constant, the mobility of the material, and the critical electric field times the square, okay. I think maybe it is cube, I forgot this exact number, it was probably cube or square. Anyways, it depends on the critical electric field, which is a fundamental material property. The critical electric field of silicon, for example, is fixed, and that is like 0.3 to 0.4 megavolt per centimeter. For gallium nitride, that is 3 megavolt per centimeter, and so on, okay. So this critical electric field is fixed. So what it means is that, and the mobility and the dielectric constants also fixed. What it means is that the on resistance and the breakdown voltage trade off with each other. If you want a higher breakdown voltage, you also will get a higher R on, which is going to affect your on state behavior. So either you get a better on state behavior or get a better off state behavior. You have to optimize between the two. You cannot get best of two, and you can actually plot this same thing, the on resistance versus the breakdown voltage, and this gives you the lines like this for silicon, for example, and then there's this technology gallium nitride, which is over here. So for a given for a given on resistance, say 1 milliohm or so, you can get a breakdown of silicon of some 100 volt. Maybe in gallium nitride you can get 1000 volt, which means for the same current you are actually getting much higher blocking voltage in the wide bandgap technology like gallium nitride. That's why the promise of gallium nitride and other technologies come up here. Doesn't mean that they are going to replace silicon just like that, because silicon has a very large market, and these power switches have their own markets. Are you talking about low voltage like 0 to 200 volt sort of applications, LiDAR applications, or some other low power sort of things, or you're talking about 200 to 600 volt applications that might include solar inverters and many of the charge the DC-DC converters, motor drives. You might also talk about 600 to 1200 volt applications, hybrid vehicles, and a host of other applications. You might also talk about locomotives and all, where you have 3 kilovolt, 2 kilovolt applications and so on. So there's a market size, there's also a cost component to it. Anyway, silicon has many devices, as I told you in the last class. IGBT, which is a vertical device, thyristors, LDMOS, CoolMOS, all these are different kind of topologies of silicon that are doing exceptionally well at the limit of the theoretical performance limit. Whereas gallium nitride, for example, the theoretical limit has not been reached because of the material problems. There's a huge research area why this is not being able to reach the theoretical limit. For example, the theoretical limit of gallium nitride is 3 megavolt per centimeter, is the breakdown voltage, but practically you only get between 1 to 2 megavolt per centimeter because of material problems and material challenges. Okay, so it has not been able to reach the full potential. There's a lot of research thrust there. The reason I keep talking about gallium nitride is because it is widely acknowledged that gallium nitride is the most talked about and the most widely prevalent semiconductor after silicon. All the white light LEDs that you see are actually gallium nitride. So that's why it's the most dominant semiconductor technology after silicon today. Okay, so this is all about power devices, and these power switches we have talked about. Basic things like DC-DC converter or inverters, all these uses these switches, and now you know what kind of things are needed. Of course, if you look into the Baliga figure of merit, a material also needs to have a high mobility. The mobility term comes there. It needs to have a high mobility to actually get a better Baliga figure of merit. So if a transistor has a mobility of 2000 centimeters square per volt second versus another transistor that has only 300 centimeters square per volt second, then you ideally would like to go with a transistor that has higher mobility, because that will give you a higher Baliga figure of merit, provided it has also a good critical breakdown voltage. Okay, so that is about power transistor that we have talked about now. Okay, enough of power transistor. Now I told you there's also other applications. If you recall, one application was the power switching that we have talked about now, the transistor and the power switching application. The second very important application is actually RF power amplifier. Okay, this is a different kind of applications, and the requirements of the transistor would be very different. For example, in the power switch I only talked about two things, that the current should be very high at very low voltage, right, and when it is off it should be blocking a large voltage here, VBR. So I only talked about the slope here, I didn't talk about the current saturating there, right. For example, in the power switch, current saturation was not talked about. Current saturation or gain was not talked about. What was talked about was the on resistance, like the slope of the IV, right, in the linear regime. So that was the power switch. Power amplifier will be a different ball game, and power amplifier has different applications and different ways. What do you mean by power amplifier? It basically RF power amplifier. So RF signals, radio frequency signals. Radio frequency signals have different bands. People in different areas categorize them in different ways, but in the RF circuits or RF devices terminologies, RF bands are divided as things like S band, L band, okay, C band, then you have X band. These are different actually bands. Okay, Q band, these are bands of RF frequencies, Ka band, and then you have more other bands like V, W bands. These are different bands of RF devices. Okay, I think first should be L and then should be S. I'll check and let you know in the next class for sure, but I think it should be L and S. So this is 1 to 2 gigahertz of frequency in the electromagnetic waves. This is 2 to 4 gigahertz of electromagnetic waves. This is 4 to 8 gigahertz. This is 8 to 12 gigahertz. This is 12 to 18 gigahertz. This is 18 to I guess 30 gigahertz, and then more. Okay, 18 to 40 probably, and then this is more. Okay, and W band is probably like 90 to 110 gigahertz and so on. So these are different frequency ranges of RF or electromagnetic signals that will come through space to your cell phone or radar or anything. The antenna will detect them. You have to actually amplify that signal, and you have low noise amplifier, power amplifier that does different kind of jobs for you. You have to amplify the signal, and so if you have an RF signal that is coming at this magnitude, if it goes through an RF power amplifier, RF PR amplifier is PA, then the magnitude will increase the same frequency. It's a very complicated device. It's a transistor, with many other passive elements will be there. So the heart of this will be a RF transistor, and the RF transistor, the important thing is that it should have a very high gain, or gain is a very important figure, and it should also have a good efficiency, right, good efficiency at actually this thing. So if you have a higher gain, higher efficiency, you are also able to at what and also at what frequency can you do that, up to what frequency can you do that. If you can amplify a signal at 4 gigahertz, doesn't mean that you will be able to amplify a signal at 40 gigahertz also, right. So there's many aspects to it, and these are RF signals that are ubiquitously used, or used all the time in your cell phones. Most of your cell phones will work between 1 to 2 gigahertz, for example. Okay, most of your cell phones will work at 1 to 2 gigahertz. So you have this wavelength, these electromagnetic waves that carry all the information into your cell phone, that gives you the internet connection, for example. You also have to transmit the signals back to the nearest base station. You need power amplifier, right. You need power amplifier to boost the signal and send. So you know, this kind of applications is used in commercial wireless mobiles, you know, in handsets you use, in handset, in base stations, mobile base stations that use this large power RF amplifiers to basically pump and send the signals everywhere. You also use them in military radars, in satellites for communication. Satellites will use that, you know, have this transmission receiving module, and then they will transmit RF signal for different kind of applications. Now again, these transistors will be exactly again the transistor. You will essentially have a source, drain and gate. So I am talking about a field effect transistor, for example. This could be your barrier layer or dielectric or oxide or whatever. You will have a source, drain, you will also have a gate, and then there will be a channel here. I am talking about field effect transistor mostly, but we can also talk about BJT and stuff like that. So this transistor will be same, but now you have to talk about gain, for example, okay, and whether it can handle RF at such high speed. Remember the power switch, you know, I was talking about on off, that typically goes in few kilohertz range to maybe a megahertz range, but here we are talking about gigahertz, and so RF signal is very different, right? It's very different ball game, and we should be, you know, generally aware of what are the things that are used in RF, what are the important. Just like we had a Baliga figure of merit, we also have an equivalent figure of merit in RF, okay, that is very important. So before I come to different technologies, I'll let you know quickly that silicon RF of course is used. Silicon RF, because it's cheap, it's, you know, it may not be the best in performance, but it is cheap, and silicon transistors for RF are definitely used. Gallium arsenide, indium phosphide, they are HEMTs, high electron mobility transistor, as well as HBTs are very widely used. One of them is definitely in your cell phone right now to actually act as a transceiver receiver module. In that module you need a gallium arsenide, indium phosphide, HBT or HEMT in your handset. Mobile base stations are now using increasingly gallium nitride HEMTs to actually do that, because, you know, this can give you better performance. Superior performance can be given, although the cost is little more. Superior performance, whether cost is a different thing, it's economy, but from the performance point of view, GaN HEMTs for example can give you superior performance. Gallium arsenide, indium phosphide can work at really high frequency applications, and silicon of course has a cost advantage. These are dominant technologies that are used in RF: silicon, gallium arsenide, indium phosphide and gallium nitride devices. They have their own, you know, things, like for example if you talk about higher bands like X band or Q band, Ka band, and of course you can get silicon transistors, but their output power is very low. You talk about output power, you talk about watt or watt per millimeter, you know, how much watt you are delivering in RF output power. So the silicon devices at very high frequencies have low output power, lower efficiency and all. So gallium nitride devices for example can have very high output power, at least 5 to 10 times higher, and very high efficiencies. So they are being increasingly used in RF now. You know, different things will need different kind of applications. Satcom, radio avionics, whether, but C band is very widely used, and silicon of course is there, but now, you know, the dominant market player is gallium nitride that is entering. So what is all about this power amplifier? So you have to essentially amplify a signal, right? You can talk about a transistor like this, you know, it's a transistor signal that, you know, this is the transistor, this is the source, this is the drain, this is the gate. The idea is that at the gate you will have a small signal, and the output you should get a large signal here. I mean, you should amplify the signal here, okay. So this is how a transistor should look like in general, and a power amplifier. What are the parameters, or what are the criteria for a power amplifier to work properly? You know, if it's a device, it's a power amplifier, it's a power transistor of course, and power amplifier will have some more elements as added with it. But, you know, if you talk about an IV characteristics, of a transistor, then what is it that you're looking for in this IV transistor that will qualify your device as a good power amplifier? Now for example in power switch, I know that I only concerned about the slope here. If the slope is good and if the breakdown is good here, then I am happy. But in a power amplifier, the frequency comes into picture and gain comes into picture, so, and output power also comes into picture. So the qualities and the parameters that you are looking at in an RF power transistor would be different from that in just a power switch for DC-DC converter, for example, okay. So let's look into this right now. So let me draw a schematic of a of a very simple, maybe a transistor. You know, I have a transistor like this. So I'll just draw a schematic here. It can be any field effect transistor. There's a gate here, okay. In the gate you might have a capacitance, the gate capacitance that you have here, right, and of course you have a lot of elements here. Capacitance will come out everywhere because it's RF signal, so capacitances actually play a very important role. This is your V in, the input voltage that you are giving, and the input voltage is very small voltage, that is a radio RF signal voltage here. You might have some inductances and other things here that I am not talking about right now. Okay, but you will bias this at gate voltage. You will apply DC bias on the gate. Of course, you have to apply DC bias on the gate, but there is also an input, an RF signal that is riding on the DC bias, that is riding on the DC bias, please remember that. Of course, the source is grounded here. Now this is drain, but on the output side also there might be a capacitance, right, and then there might be a load resistance, right, there might be a load resistance here, and of course there is a VDD, that is the drain bias, the supply voltage, that might also have an inductance or other elements here, but that's okay, we don't worry about that. So what happens here is that small riding voltage V in will lead to a large change in the what is it called, the ID, the drain current that is flowing in this direction, right, the drain current that is flowing in this direction, that is ID. You will get a large swing, it is called a swing, you will get a large swing in the drain current here, and that large swing in the drain current will lead to a large swing in the drain voltage VDS. A large swing in the drain voltage can be there. This is the drain, this is source of course, but I am just talking about the VDS. There will be a large swing in the drain voltage here, and if there is a large swing in the drain voltage, then there might be a large swing in the output voltage. This is your output voltage. Okay, this is the output voltage. So in the output voltage also you get a large swing, although you are feeding inside a small swing in the input, you get a large swing in the output. Okay, that's how the basic schematic of an RF power transistor looks like. So what happens is that you have for example the ID VD characteristics here, the ID, and then the VD characteristics, right, ID VD characteristics. Let me actually draw it in a different page maybe. So you have the ID, the drain current, right, and then you have a drain voltage here, right, and you have this you have this ID VD family of curves here, right, sorry, you have this family of curves here, okay, like that. Okay. So what happens is that if you look, and this called the knee voltage, right, where it is bending essentially, and this is suppose your breakdown voltage, your device will break down here. Okay, your device will break down here, maybe it's heating or whatever is breaking down here, over here. Then you have your window in which your voltage can have a swing. This is the swing in which your voltage can be, this is the maximum voltage swing you can have. On the output side, the voltage swing can be maximum this, it cannot extend beyond that. Okay, this swing has to be there. This is called your voltage swing. Okay, this is your voltage swing. If it goes above, then it will break down. If it goes below here, you cannot get gain, right. So this is your voltage swing, and similarly you will have your current swing also, and the current swing will be between the maximum current you have here, which is this, and this 0. So your current swing, if I draw it here, the current swing will be right, this is your current swing. Okay, your current swing will be there, it will be between the highest point and the lowest point here. Okay, so that is your current swing and that is your voltage swing, and ideally you will have a load line, that is the operating bias of the device will decide this load line along which you are dividing, and the slope of this load line actually is the optimum output resistance, the load resistance where you will have the device loaded. And the saturation is very important in this device, because you see your power is your swing is limited up to here, that is where the device the device saturation starts from here. If the current does not saturate, for example if I take ID and VD and the current does not saturate, it is all like this. If there is no saturation of current, then how will you define the voltage swing? The voltage swing will have to be defined from this 0 only, 0 to here whatever, then your output power will be 0 because your voltage is coming to 0. Okay, your voltage is coming to 0 and your current also will come to 0, because you cannot define a swing in the current, which is the swing. So it will be everywhere, right, like it does not have a low value and a high value. If you put the swing here, it will be something like that. If you decide the voltage to be here, then your swing will be like that and like that and like that. So eventually you can get no power at all. It is very important that your device saturates in power in the ID VD, so that you can get a swing in the voltage as well as a swing in the current, and there is a slope here, the load line. This load line essentially is manifestation of the current here. So, there is a current flowing here, and there is a load, the resistance you are putting, the optimum resistance will decide where you are biasing the device, so that you can get the maximum swing. Okay. So, what I mean is that, suppose what I mean by that is that I will just draw a small schematic here. Okay. I will just draw a small schematic here. Suppose this is your IV, okay. This is the IDVD characteristics, this is breaking down here. Okay. So, to get maximum power, you would want to bias at the middle of this, so that you get the maximum swing here, you get the maximum power, and so you are biasing at some midpoint here, right. Suppose, because that is why you are able to get both the swings on middle of middle, right. But if you are biasing, you are not biasing the device here, you are biasing the device, for example here, your device operating point is here, then you will be able to get only this much swing. The other swing can be more, but you will not get the optimum power here, it will swing, and similarly your voltage, your current swing will also be less, right. So, you want to maximize the product of the voltage and the current swing. So, you have to get the optimum load line where you operate, only then you will be able to get the gain, and so current saturation is very important here. And one of the important terms that you call in this type of device is called drain efficiency, DE. The drain efficiency is basically what is the RF output power you are getting, divided by what is the DC power you are putting in. Okay. That is one important parameter. And then another important parameter is called power added efficiency, okay. Power added efficiency, which is called PAE, that is defined as what is the output RF power minus what is the input RF power, because input also you are giving a small swing, right, divided by what is the DC power you are supplying. That is called your power added efficiency. That is a very important number. And the output power, maximum output power you will get from such a device is given by the breakdown voltage here. This is the breakdown voltage, and this is the knee voltage, right, this is the knee voltage. So, the swing is limited between this, no. So, it will be breakdown voltage minus knee voltage, because that is the swing you are getting, square divided by RL, the load resistance optimum, this swing, okay. That takes into account the current also, by the way, okay. So, this is your the maximum output power that you are going to get from the power transistor, okay. To work as a power transistor, of course, it depends, many of the important things are there. One of the things that is there, which we shall not discuss here in much details or anything, is called small signal model. So, small signal model will tell you how fast the device can work. The two parameters I called you, FT and Fmax. Ft is defined as the current gain cutoff frequency, that is the frequency at which the input and the output current will be of the same magnitude, so that your gain becomes 1, and output Fmax is defined as that frequency at which your input and output power will be the same, so it is called power gain cutoff frequency, okay. So, now HBTs and HEMTs will have their own distinct and sort of or FETs will have their own small signal model that will tell you the expression for exactly this cutoff frequency for FT or cutoff frequency of Fmax. You can get that cutoff frequency expressions. I will not write that down here in this course, it is not relevant, but a higher FT means that in general it tells you about the speed of the device. Higher Fmax tells you at up to how much frequency you are going to get some power. So, for example, if your Fmax is 200 gigahertz, it means at 200 gigahertz you are going to get a gain of 1, which means there is no gain after 200 gigahertz. So, all your gain will happen at frequencies lower than 200 gigahertz, okay. So, that is important thing. And the most important transistor parameter, now you might ask, I have a transistor, I have a source, I have a drain, and I have a gate. Okay, it is good that you told me about the drain efficiency, the RF, the load line, the swing, the power added efficiency, all things are good. But from the transistor point of view, what is that parameter that needs to be high or that needs to be low, which actually decides how high the FT will be, or how high the Fmax will be, or how better you will get the power devices and all this thing, is called transconductance, or GM. You have heard this and you have learned about this long back. Transconductance is defined as the output current, the derivative of the output current with respect to the gate voltage, okay, at a particular drain voltage, okay. So, the transconductance needs to be very high. At high transconductance means that you will get a better frequency response or a higher speed device. Okay. And along with transconductance, you will have many parasitic elements, the resistances and the capacitances that are there in the circuit. For example, the source and drain will have some contact resistance, some channel resistance. All this will contribute to parasitic resistance. And similarly, the big pads of source and drain and all, they will also work as capacitors, and so you will have some large area capacitances also. So you know that all the parasitic resistances and all the parasitic capacitances, their multiplication gives you this time, which is the time constant. Those are time constants that increase the delay of the device from its intrinsic performance. Okay, they delay the device from an intrinsic performance. So your Ft and Fmax, you know, you have a big expression, but in general, if you talk about, you know, just like a Ft of a Hemth or a just like you know, you have a Hemth or a Ft, then Ft will depend on Gm, and then you have many capacitance resistance products like CGS times some RSD, then some gate drain capacitance times some R source drain resistance, and so on. There are many expressions here. In a way, all these are parasitic resistances and capacitances that will actually tend to reduce the frequency response, that will tend to reduce the speed of the device. Okay, that will tend to reduce the speed of the device. You need to make sure that your mobility is high, electron velocity is high, the parasitic resistances, capacitances are low, and your GM needs to be very high in order to get a better speed transistor. Okay, so for example, if you plot the gain of a of an RF transistor, and the gain is plotted in dB, if you plot the gain as a function of frequency here, then you know it's a dB, of course, the gain will stay flat and then drop at a rate of 20 dB per decade. So the gain is dropping by 20 dB in one decade of frequency. So this is a log scale of the frequency, by the way. So you will have, say, 1 gigahertz, 10 gigahertz, then 100 gigahertz. These are one decade. No, so 20 dB it will fall per decade, the slope with which it will fall. And you know, if the gain becomes 0 dB, which means the gain is 1, log of 1 is 0, right? If the gain becomes 0 dB, that point, and if this is the current gain frequency, right, then you will define this particular point as the Ft. Okay, where the gain becomes 0, where the gain becomes 0. Typically there is a parameter called H21, it's an H parameter that you plot. Let's not go into that. And this plotting of the H21 parameter, this is actually like the gain, the current gain, and wherever it becomes 0 dB, that point is called your current gain cutoff frequency. And typically that is how you decide, you know, you can do these measurements in a vector network analyzer to find out how the device works and so on and so forth. Okay, so let's end up the class here. So we have now studied also RF transistors. Now we have studied you know, power and RF both transistors. There is a little bit of RF transistors still remaining in the, that we will cover in the next class. There is an important figure of merit from the transistor point of view, not the circuit point of view. Okay, from the transistor point of view, there is a figure of merit, just like you had figure of merit, a Balliger figure of merit in power switching. Similarly, in RF devices, there is also a figure of merit called Johnson figure of merit, and the Johnson figure of merit will tell you how better a material or a device can be for power amplification. Okay, high power, high speed RF transistors. Okay, so we will discuss about power Johnson figure of merit and the different competing technologies, and you know, what are the things we should keep in mind if we want to design a better RF transistor, for example, apart from the obvious, which is reducing the parasitic capacitance and resistances, but from the device point of view. Okay, and then we will decide, and then we will go forward in the next lectures to things like transistors for memory applications, transistors for logic, which is basically nothing but CMOS that you know, and then maybe in the last 1 or 2 lectures we will, you know, quickly discuss what are the steps in practical life in fabrication world to make these devices that we have studied till now, very briefly. And if time permits, we will solve some question papers of some popular entrance exams, so that you will get some feel of how to do numericals associated with this whole course. Okay, so we will end the class here today. Thank you for your time.